Welcome to Physics Uncomplicated. Sit back, relax, and enjoy as you learn the key concepts of physics. Each chapter in this series is intentionally kept to a maximum of 12 minutes to convey only the essential facts and ideas for that particular topic. You may use these videos as a supplementary aid to refresh your understanding of the chapter. Wishing you all the best.
Before we start our chapter, let's take a moment to introduce the characters who will appear throughout this animated series in both the Class 11 and 12 videos.
Hey Em, today's physics topic is motion in one dimension.
Sounds simple, but I bet there's more to it.
Good morning, class. Today we explore how objects move along a straight line. It's called motion in one dimension. Consider a ball rolling across a floor, a train moving along a straight track, or an elevator traveling up and down. These examples illustrate motion in one dimension, movement along a straight line, either in one direction or the opposite. Before we go further, let's understand the actual concept of rest and motion. If any body does not change the position as time passes, then it is said to be at rest. For example, the rock in this video continues to stay firm on the ground throughout the seasons. Motion is a property that involves both the observer and the object being observed. Let's visualize this with an example. A boy is watching a train pass by. From his perspective, he is at rest while the train is in motion. Now, if we switch perspectives and consider a passenger sitting inside the train, she is at rest, and the world outside her window is in motion. Let's now understand the concepts of position, distance, and displacement. To follow the path of the shark, it begins by rising from behind the rock and moving 4.5 units along the y-axis. After that, it moves forward along the x-axis and ultimately stops at an x-coordinate of 8.3. From this example, we can determine that the shark's final position is 8.3, 4.5. The distance traveled by the shark is represented by the length of the trace, indicated by the black dots. In contrast, the displacement is defined as the straight line distance between the origin and the final position. With this understanding, let's move on to our next topic, average and instantaneous speed. Assume a rickshaw moves through the city traffic. The rickshaw does not maintain a uniform speed throughout its motion. The speed varies with time based on traffic conditions. Let's say the rickshaw travels a distance of 30 meters in 6 seconds. The average speed of the rickshaw can be calculated by dividing the distance traveled by the time taken. This average speed represents the net effect of the rickshaw over the specified time. In this case, the net effect is covering a distance of 30 meters in 6 seconds. During a 6-second journey, it's clear that the rickshaw does not move at a uniform speed. To calculate the speed of the rickshaw at a specific moment in time, such as at the 3rd second of the journey, we need to adopt a different approach. It is easier to visualize instantaneous speed if we plot a graph of the distance traveled by the rickshaw as a function of time. To understand instantaneous speed, let's divide the time on the x-axis into 6 seconds and the distance on the y-axis into 30 meters. Before we discuss instantaneous speed, let's calculate the average speed of the rickshaw between the 2nd second and the 5th second. From the graph, we can see that the distance covered at 2 seconds is 8 meters, while at 5 seconds it is 24 meters. If we connect these 2 points on the graph, we will form a line. From high school geometry, we know that the slope of a line is defined as the ratio of the vertical change to the horizontal change between 2 points on the line. In this case, the vertical change represents the distance traveled between 8 meters and 24 meters, while the horizontal change corresponds to the time interval between 2 and 5 seconds. So, the slope of the line gives us the average speed of 16 divided by 3, which is 5.3 meters per second. Instantaneous refers to something that occurs at a specific moment in time. For example, if we look at a clock that shows time down to the milliseconds and need to determine the instantaneous speed at 3.5 seconds, we should evaluate it exactly at 3.5 seconds, not at 3.49 or 3.51 seconds. In simple terms, it refers to the measurement at a precise point in time. From the previous example, we calculated the average speed between 2 and 5 seconds. In order to calculate the instantaneous speed at 3.5 seconds, we need to reduce the time period to a precise point of 3.5 seconds. And the slope of the tangent drawn at this point gives us the instantaneous speed. Let's now move to the next topic, average and instantaneous velocity. Velocity refers to the speed of an object in a specific direction. For example, consider an auto rickshaw moving at a constant speed in a certain direction. If the rickshaw changes direction while maintaining the same speed, its velocity also changes. This is because velocity is a vector quantity, which means it has both magnitude, speed, and direction. Let's illustrate average and instantaneous velocity on a graph. Consider a body moving from point A to point B. Let's assume that the time at point A is t1 and the time at point B is t2. The average velocity of the body is defined as the displacement vector from A to B, represented as AB arrow divided by the elapsed time, which is t2 minus t1. This calculation shows how fast the body moves from position A to position B. We know that displacement is the straight line distance from the origin. Assuming the origin is point O, let's draw a straight line R1 to point A and another straight line R2 to point B. From the diagram, we can conclude that the net displacement of the body, represented by the arrow from A to B, can also be expressed as R2 minus R1. Similar to instantaneous speed, instantaneous velocity can be defined geometrically as the slope of the tangent line drawn on the displacement time graph at a specified moment. Acceleration refers to the rate at which a body's velocity changes. This change in velocity can be classified as positive, which indicates acceleration, or negative, indicating deceleration. For example, consider a rickshaw that initially accelerates, but then slows down when it hits a speed bump. In both scenarios, whether it is speeding up or slowing down, the rickshaw is still considered to be accelerating. When analyzing motion in a straight line with constant acceleration, we use a set of 5 equations known as the SUVAT equations. These equations help us relate 5 key quantities: S for displacement, U for initial velocity, V for final velocity, A for acceleration, T for time. Each equation connects different combinations of these variables, enabling us to solve motion problems even when some values are unknown. It's important to remember that these equations are only applicable when the acceleration is constant. They serve as a powerful tool in kinematics and form the foundation for analyzing motion. When a body is falling freely, it is subjected to gravitational acceleration of 9.8 meters per second squared. In these SUVAT equations we learned previously, we use a value of negative 9.8 meters per second squared to indicate that the body is moving in the negative y direction. Thank you, class. That's a wrap. We will meet in the next class to discuss motion in a plane. Bye.